Right. And put this little bandy over her. Good. Now we are recording. Notes page 28 to 30. We're going to learn a little something about them vectors. Let's go. Got my coat on because I'm ready to go in case anybody comes in. We're ready. Don't eyeball me. All right, let's go. Let's learn about vectors. Nice thing about vectors, they're kind of intuitive. They're just arrows. Arrows tell you things. Here we go. Vectors represent physical quantities that have magnitude and direction. We've done a number of examples of these, which you well know already. Displacement, velocity, acceleration, magnitude and direction. Magnitude, of course, is just a number in a unit. Direction is just which way it's going. So how do we draw them? Boom, arrows. What's an arrow? There's a definition over there if you're not sure. It can represent any vector physical quantity, like those three we had up top there: displacement, velocity, acceleration. What do we know so far? Oh, well, what a surprise. Displacement, velocity, acceleration. By the way, we've talked a lot about different velocities. We've talked about initial velocity, vector, final velocity, vector, change in velocity, vector, average velocity, which we've written a couple different ways, including bold with the bar, vector, or we've even trying out V with the bar hat. I haven't seen it in any textbooks, but anyway, vector. Okay, so how do these arrows actually make sense of it? They're pretty easy. Magnitude note. Magnitude is the amount. That's the 20 meters per second, or the 3 meters per second squared, or the 12 meters. Magnitude note. The length of the arrow. This is the full length of the arrow. Tip to tail, they call it. Represents the magnitude of the physical quantity. It's a pretty straightforward thing. Here is an arrow. This arrow could represent a displacement, let's say. Well, that's a bigger displacement. If this arrow instead represented velocity, well, now that's a smaller velocity. If this arrow instead represented acceleration, well, you see your acceleration, there's a bigger acceleration. There's a bigger acceleration still. And in fact, we will use the length of the arrow with a scale. And the scale, of course, is defined over there in your vocab bar as well. A scale. So this is not a scale that you weigh your fish on that you caught over the weekend, but a conversion scale. So for example, if this arrow were 7 centimeters long, then you would have some sort of conversion scale that says 1 centimeter equals 2 meters per second squared. And that would then give you 14 meters per second squared as represented by this arrow, whereas maybe this one would be only 7. Okay. Direction. This is even easier. Which way it points is the way it goes. That's the direction of the physical quantity. So this acceleration is to the right. This acceleration is the same magnitude down. This velocity is down. This velocity is hopefully the same magnitude up. That's all. So best thing to do with vectors is what we're doing right here. Diagram. All right, let's come over here. Let's do a couple examples. So these are very simple, very straightforward, but do the simple and straightforward correctly, and then you'll be comfortable when it gets more complicated, huh? Okay, let's go. So this, if 1 centimeter represents 5 meters, there is your scale. That's a conversion factor. In fact, the best way to write that is just something like this. 1 centimeter equals 5 meters. And then we'll use that as a fraction. Okay, draw a vector that represents 35 meters west. Now, the official way to do this, most of you just put your brain on it and you'll figure this out no problem. Oh, if 1 centimeter is 5 meters, then 35 meters, of course, is, well, it's a factor of 7 centimeters. However, let me give you the official way to do this, because one day you may need that official way to do this. The official way, write what you're starting with. You're starting with 35 meters. Now, multiply by a fraction. Get your units in there. You want to convert from meters, so they cancel. Put it in the denominator to centimeters, in the numerator, and then put your numbers in there. The centimeters carries a 1. You get no choice, so put the 1 next to centimeters. The meters carries the 5. You get no choice. Put the 5 next to the meters. These cancel. Boom, boom. And of course, you get 35 over 5, 7 centimeters as a length, as we expected. Okay, so how do we actually do this? You got to draw your vector carefully, because if you make it too long, it doesn't represent 35 meters anymore. It represents some different length. If you get it too short, it doesn't represent 35 anymore. So here's my little ruler, which should roughly match the scaling of your ruler at home, I hope. Anyway, easiest way to do this is put a mark. We want a 7 centimeters, so I'll go put a little dot at my 0, right in there, and I'll put a dot at my 7.0. There it is, and I'm going to connect the two. And actually, the way you'll do this is you'll connect these, keep your straight edge sharp, and you'll connect these like this. Okay, try to make it as exact as you can. I know I'm a little off, but you can do better on your paper. Make it as exact as you can. Get this out of the way. So far we have a stick. Good. We have a stick. That's not yet a vector. See, it has a length, which means it has a magnitude, but it doesn't yet have a direction, so you got to put an arrowhead on it. And the key is you don't want the arrowhead to extend the length of your vector. If you come over here and you're like, oh, look at that idea. Oh, well, by the way, which way is west? Here's north. You have to have a definition. North is up. So you can make your little compass over here. Never eat soggy worms, or however you remember this thing. West is going to be the left. You come over here like, oh, cold. You just killed it. You just killed it. Yes, it's west, but it's the wrong length. Your sloppy arrowhead now made this 8.2 centimeters long. That is not 35 meters. This is no longer correct. So how do you avoid being sloppy? Drag away. Watch this now. Come on over to your arrowhead. Just get your pen tip, pencil tip, right to the edge there. Wait, right there, and then pull back. Right to the edge and pull back. That way, it indicates the correct direction, but I did not make it any longer in the process. In fact, if I put my ruler back up here, I should find that this is still just about 7 centimeters. Good. In fact, I'll color this whole thing blue. Why not? Nice. There we go. Okay. Good. There is 35 meters west. And you can label it if you want. 35 meters west. However, your label is really not that important. The reality is, I need to measure your vector. So it has to point the right way, it has to be in the correct length, and boom, then it's good to go. So let's go down here. 1 centimeter represents 5 meters per second. Draw a vector that represents 35 meters per second west. Okay, well here, our conversion factor, now our scale, just like before, is a 1 to 5, except this time it's 1 centimeter represents 5 meters per second. Okay, so we can do our little conversion over here on the side. In fact, it is almost identical to what we did before, so you don't really need to rewrite it. I could bring it down here. The only difference here now is that this is meters per second, and this is meters per second, and those will cancel out. And you're left with a 7 centimeter vector again. So we come on down here and draw this again. You can do that just fine. I'm going to make it easy on myself and just clone this since I already made one. Bring it down here, and it's still wet. This one I'll color it green. So I don't want to make the vector any longer. I want it still to represent 35 meters per second west. I go to the tip, pull back, boom, there it is. Good. This is 35 meters per second west. Done. And then finally, we have this for another problem that looks quite similar. Here's our scale. 1 centimeter represents 5 meters per second squared. Oh, well now our scale actually converts between a scale length and an acceleration. We need 5 meters per second squared. How do we do the conversion? Well, listen, really have to do it again. It's really basically the same thing, except, oh, I lost it. Let's try it again. Might end up being easier just to rewrite it. You're gonna grab it. Come on now. Yeah. Yeah, there we go. Now it's actually in meter per second squared that it's in. And the conversion factor includes a meter per second squared, but you still get the same cancel. You get your 7 centimeter length, boom, done. And so you should measure it again, but I'm just going to clone it. Come on now. Maybe I'm going to clone it. Good. Bring it on down here. It doesn't believe in the ethics of cloning. And so this one, make them red. Put an arrowhead on it. Where you just pull. Oh. Uh-oh, did I change the length? Gotta be careful about that. Oh, good. Pull back from the tip. Boom, boom. And this one represents 35 meters per second squared wet. Okay, we got 3 arrows. Though they are different colors, they look quite similar. And so we have the key question, are the answers the same? Are the answers the same? Are the answers, yeah, they're all 7 centimeters to the left or other. No! No, they're not all the same. Dang it. No. One represents displacement, one represents velocity, one represents acceleration. They are not the same thing. 35 meters is not the same thing as 35 meters per second, which is not the same thing as 35 meters per second squared. Completely distinct. Completely distinct. 35 meters is how far you could walk in a very short time. 35 meters per second, you will never walk that speed in your entire life, at least not relative to the ground. So, just beware. Vectors stick with their own kind. So displacement vectors like to hang out with displacement vectors. Velocity vectors like to hang out with velocity vectors. Acceleration vectors like to hang out with acceleration vectors. There's no mixing. Okay, let's go. Oh, too far. Back one. Here we go. Here's one at an angle. Starting at point P and using a scale. Oh, look at this. Nice little scale. 1 centimeter equals 2.5 meters. 1 centimeter equals 2.5 meters. Draw a vector that is 10 meters at 60 degrees north of east. Okay, we'll pull north up on the paper. Typically we do that. You don't have to do that. It's not right. North is not up. Okay, so let's go with this. 10 meters. Let's get our 10 meters in order. 10 meters. We want to convert this into a scaled distance. You can't draw 10 meters on your piece of paper. Even my big paper here on the board is nowhere near 10 meters. So we got to get this into a scaled size so we can actually draw it on the paper. Here's our scale factor. We want to get rid of meters, cancel, and get into centimeters. Okay, good. Actually, I can put my units in green. Let me do that. Then you have no choice. You've got to put the numbers and go with them. Centimeters carries the 1. It goes with it again. Meters carries the 2.5. Goes with it again. Cancel, cancel. And the answer is 10 over 2.5, a 4 centimeter vector. Now you can't just come over here and start drawing 4 centimeters. Because in this case, the direction is 60 degrees north of east. Well, it's good to think about that for a second. If north is up on the paper, east is to the right, north of east is come up this way. So we're going to be somewhere like in this direction. Here's our 60 degrees right here. So how do we get that 60 degrees? Come on in, protractor. Ba-boom. Get it lined up right on that point. Mark yourself some 60 degrees. If east is off in this direction and north is up here, we want to get 60 degrees north of east. Let's go with it. So here's 10, 20, 30, 40, 50, 60. Just count. Who cares what the numbers say? Just count. 60 is right here. That's 60 degrees north of east. Now, you have a combo ruler protractor. I have just a ruler. I have to now come over here, as do you, and line this up and go in the direction of that dot. So we're lined up nicely now. But, by the way, this dot's a little big. Typically, the dot should be smaller. We'll go from the middle of the dot. Okay, we want to go 4 centimeters, as we've determined right here, in the direction of that dot. We're not going to go all the way to the dot. The dot's at the 6-something centimeters, 6.3 centimeters on mine. So we're not going to go all the way there. We'll go part of the way there. So I'm going to draw right along this to the 4 centimeter mark, which on mine is right about, maybe there. A little short, but that's okay. It's hard to see on it. I'll move it up just a pinch. Good. Okay. Get this guy out of the way. Move this over a little so it doesn't interfere. This is a displacement. I think we've been drawing those in blue, so I'll make it blue. One needs an arrowhead. Go to the tip, pull back. Go to the tip, pull back. Boom. There it is. Done. I think yours roughly will end up there. I tried to make this ruler here roughly the size of yours. Okay. How do vectors combine in 1D? All right, check this out. So we just drew singular vectors. Now we're going to put them together, which is a pretty easy process. When multiple vectors combine, we call them adding. When we add them, they actually can make one big one. It's pretty cool. Put the little ones together, you make one big one. The big one is the result, and so we give it the name, the resultant. All right, well, you need to be able to move them in order to combine them. For example, I'll take these three over here. If these three vectors are just kind of hanging out in space and I say combine them, well, it's a poof. What do? You have to be able to move them. You have to move them so they link up with each other. Oh, that linked up. And oh, that linked up. Once you move them so they link up, you can actually then create this thing called the resultant, this combination of the three. It's a pretty new thing. So this process of moving them around, just like in math class, this is called translation. But the key is they must remain the same length and point in the same direction. Changing length, by the way, from math class, we call that dilation. Changing direction in math class, we call that rotation. You must keep the length and direction for, of course, the reason that length tells you the magnitude, direction tells you the direction. So if you change the length, then it's not 35 meters anymore. If you change the direction, then it's not west anymore. So you have to try to maintain. Maintaining the length is not that hard. Maintaining the direction, sometimes it's good in your head to look at the arrow and just repeat for yourself, which way is this thing pointing? Well, this thing is pointing up and to the right. You can even call it UR, upright. If you remember it's up and to the right, then when you translate it or move it, you are more likely to be accurate. And here's the thing. It looks easy for me because I have a smartboard and I can translate. You, however, do not have a smartboard at your desk. And so your translation will actually look like this. If we take that up and to the right arrow, and you don't want it here, you want it over here, you're just going to have to say, it's about this long, and I'm going to have to go draw it over here. You have to redraw it and cross this one out. So for you, you really have to pay attention to roughly how long and roughly which way it's going. Okay, so let's go over here. Step 1, use translation to orient your vectors so that they're head to tail. Okay, let's take these three. All right, right now, are these head to tail? No, the head of one must touch the tail of another. So the head is here, the tail is here. Let's bring it over here. Now that's head to tail. Sometimes call that tip to tail. Now this one, orient this one. So it's tip to tail. Cool. Now those are head to tail or tip to tail. At the end, there should be, it says underneath there, only one exposed tail and one exposed head. That's fine. Here's the exposed tail. We circle that. That's our step here. Here's our exposed head. We X that. It's over here. So it's called circle to start, X to finish. Circle to start, X to finish. You start at the tail, then you follow the path. This arrow brings you down here. The next arrow continues you here. And the third arrow continues over here. That's where you finish. X marks the spot. The resultant is actually the arrow that's drawn from the circle to the X. So from here to here, the shortcut, the displacement, if we're working with displacements, that is your resultant. In fact, I have one pre-drawn right here. And let's line it up. Get the sizing right. Right there. Boom. There it is. Now, there's something really cool about this, and here's what it is. No matter what, you get all this junk out of the way. No matter where you put these, no matter what order you put them in, like for example, we'll start with this one, we'll go to this one, and we'll end with this one. Play the same game. The exposed tail, circle to start, X to finish. The resultant is, boom, the exact same thing. Magic. No matter which order you do these in, maybe we'll do this one first, we'll do, get out of here, we'll do this one second, and we'll do this one third. The beauty is it doesn't matter. Circle to start, X to finish, that's the finish, and the resultant is, boom, the exact same thing again. That one looks like a funky heart. Anyway, there it is. And the way you would define this green resultant is by its length and its direction. So ultimately, if you needed to, you bring these two along. Oh, hold on now. You bring these two along, and you would say, oh, well, what's the resultant of those three? Draw it out. Slap this thing on here. You get its length. It's a scaled length generally. And then you'll have some sort of axes here, and you can rotate this thing around. You can say, oh, well, this one is, maybe if this is set up like this, and wherever it comes through, and something like, move this ruler out of the way. This is very thick. Of course, you'll write this much neater, but this is somewhere like, I can count, 10, 20, 30, maybe it's like 32 degrees south of east, something like that. Okay? That's how it all goes down. All right, so let's look at a couple of simple examples. What I was just showing you was basically a two-dimensional example. You're only going to be dealing with one-dimensional examples right now, which really makes this whole process even a fair bit easier than what you're seeing. So, let's go. Let's determine the resultant in these different scenarios. Okay, the resultant of the three vectors shown. Each vector has a magnitude of 6 meters. So this one is 6 meters to the right. This one is 6 meters to the right. This one is 6 meters to the right. Algebraically, you could set this up with givens of units. So you can have these are all displacements because they're in meters. So we can number maybe 1, 2, and 3. Displacement 1 is 6 meters to the right. We can call right positive. Displacement 2 is 6 meters to the right. Displacement 3 is 6 meters to the right. And they're asking for the resultant displacement. So you can even call it displacement R for resultant. And as we said before, you're actually adding them. So the resultant here would just be D1 plus D2 plus D3. Of course, 6, 6, 6 gives you that mark of the beast, 18 meters. The other way to do this, though, which I want you to practice, I know it's very easy here, but do it anyway. The other way to do this is to translate, pick them up and move them. So let's keep one in place. They're not head to tail right now. Notice their heads and tails are separated. Let's make them all head to tail. Let's leave number 3 where it is. I'm going to redraw number 1, head to tail with 3. So let me put it should be to the right and roughly this long. I'm not measuring it, doesn't have to be exact. Now, since I moved it, I'm going to hash it out. It's not in both places, it's only in one. Then I'm going to move 2 to the head of 1. It's about this long to the right. There it is, 2. Hash that one out. If you want to, you can redraw your 6 meters and your 6 meters. Now, basic rules. Once they're head to tail, circle the start, the exposed tail. Follow it. X to finish. Your resultant is that. You can draw it right on it. You can draw it just below it. There's the resultant. And of course, that resultant displacement is going to be 6 plus 6 plus 6, 18 meters to the right. Done. How about this one here? Determine the magnitude of the resultant of the two vectors shown and draw the resultant. The longer has a magnitude of 5. So this one is 5 meters. You can call this one like up and to the right. And this one is down and to the left. In fact, you can see they're exact opposite directions. So that kind of helps us a little bit here. And how long is that one? Both are drawn to scale. So that's actually helpful. If we bring our ruler down over here, what you will see is this one is about 4.5 centimeters. I think in your paper it might actually be 5. I'm a little off on the scaling with this drawing. And this one is 2.25. I think it's 2.5 on yours. But anyway, it's half the size of the other, which means it must represent 2.5 meters. And so if we wanted to do this algebraically, we could say, move this. We can say up and to the right would be our positive, and then opposite that, down and to the left would be negative. And so these are displacement. So the displacement 1, so this one 1 and this one 2. Displacement 1 is positive 5 meters. And displacement 2 is down to the left, negative 2.5 meters. Displacement resultant, question mark. Put your little hats on there. And the equation, of course, just add them up. This is what vector addition looks like. Now, it'll get a little more complicated when we have 2 dimensions, but for right now, this is easy. D1 plus D2. And, of course, substitute and solve. The resultant is going to be 5 meters plus negative 2.5 meters. Of course, gives you 2.5 meters in the positive, which is up and to the right. Drawing these, come over here, play the same game. So notice these are opposed to each other. Maybe we want to leave the big one alone, move the little one. Make it head to tail. So it's about this long, about half the length, and it points down left. This is where it's good in your brain to say down left, down left. Let me bring it up over here. I'm going to make it head to tail. I'm going to stick it right on the head of this one and go down left, about halfway back down. I know that may look a little awkward, but follow it. Exposed tail, circle the start, then it turns you back around, exit finish. There's the finish. Your resultant in this case is from the circle to the X. That's it. Follow the protocol. The resultant is circle to X. It's up and to the right, and it's half that distance. There's your 2.5 meters up, right. Good. All right, let's look at a couple examples over here, and then we'll be all done with this. None of these are too magical. Carl. All right, Carl. Got an airport people mover in various states of motion. Thanks, Carl. Okay, the people mover itself travels at 1.5 meters per second forward. Forward! Well, positive. All right, so Carl's running through the airport. I'm going to solve this both ways. His own leg speed. So the velocity of Carl is 4.5 meters per second. He's also going forward, so we can call him a plus. The people mover, he's on the people mover, but the people mover itself, it's called the PM, the people mover, is going forward at 1.5. What's Carl's resultant velocity? Well, go to the equation, you're just doing vector addition. Velocity of Carl plus the velocity of the people mover. And of course, that's an easy one. 4.5 plus 1.5, you get 6 meters per second forward. I'd also like you to draw this. And this is a sketch, so you don't have to get crazy. It's a sketch. So Carl's velocity is 4.5. Let's call forward to the right here. So Carl's velocity will be like this. This is the velocity of Carl. And then the people mover's velocity is 1.5 to the right. But you know what? Why draw it? 1.5 is only a third of this, so it'll be short, like something like this. But why draw it here? We want this thing to be head to tail. So why not just straight away, boom, make it head to tail. There's another 1.5. There's the velocity of the people mover. His was 4.5. This was 1.5. Play that game. Circle the start. Exit finish. That was that finish. The resultant is you can draw it wherever you want. Remember, you're allowed to translate your vectors. So if this is a mess, feel free to come down here and just say, aha, there's my resultant velocity, 6 meters per second to the right. Good. Good. Okay, let's keep on going. Realizing he forgot his passport, Carl turns and runs at 4.5 meters per second in the long way on a people mover. You ever do this? Huh. Let's use the same. Forward is positive this way. So now Carl's velocity is in the backward direction, negative 4.5 for what his legs are taking him at. The people mover, though, does not care. It's still positive 1.5. And we need a resultant velocity. Of course, if you do this with the equation, you add the 2. And I'll just jump straight to the substitute solve. And it is negative 4.5 plus 1.5 gives you -3. So Carl's going to be going 3 meters per second backward. That's his resultant velocity. I'm going to draw this, which I'd like you to do. This time, Carl is going 4.5 meters per second backward. The people mover is still 1.5 forward. Now, you may want to put it over here, but you're going to have to move it. We want it head to tail. So don't bother. Why don't you just make it head to tail straight away? Come back over here, come back this much this way. That's the velocity of the people mover. Carl's velocity was 4.5. The people mover was 1.5. Exposed tail, circle to start. X to finish. Your resultant is circle to X. I don't care which way the last arrow went. That's not the protocol. Circle to X. There it is. Boom. There's your arrow. So 4.5 minus 1.5 is your 3 meters per second backward. Good. On his way, Carl's exercise-induced asthma kicks in and his running slows to 1.5 meters per second. Still the wrong way on the people mover. What's his resultant velocity? So now Carl is at -1.5. The people mover is at positive 1.5. And the resultant is that we're trying to find. Meters per second. Of course, we jump to the substitute solve. The resultant will just be Carl's velocity plus the people mover's velocity. 1.5 and -1.5 gives you 0. This is 0. And if you drew this one out, Carl now is going backward at 1.5. There's Carl's velocity. The people mover is going forward, head to tail it at 1.5. Here, well, you kind of pick one of the tails to start with. You can kind of see what's happening here. If we follow it, it brings you right back. Boom, you go right back to the start. There is no circle to X. There is no length. The resultant velocity here, that's an R, is just 0. Good. Last question. Finally, Carl passes out and is slumped on the people mover. Poor Carl. He just wanted his passport. What's his resultant velocity? So Carl's own leg speed's at 0. The people mover, no sympathy. It's still at 1.5. Of course, you run this thing, you can tell the resultant velocity will be just the people. So 0 plus the people mover is just going to be the people mover, 1.5 meters per second. And of course, if we drew that, Carl is nothing, and the people mover just chugging along, 1.5, and it's still circle to start, X to finish. The resultant is right there. Resultant velocity is still 1.5 meters per second forward. Okay, so here's an important note. Focus on this note. This note says, come on, highlighter. Give me any love? Maybe not. Anyway, when an object, there we go. Oh, we are getting some love. When an object has a constant velocity, it can be at rest or it can be in motion. Either way, it's equilibrium. Either way, it's equilibrium. In fact, here, in all of the situations above, all of the situations above qualify as equilibrium. That does not mean the individual parts of Carl's body are in equilibrium, but Carl as a whole is in equilibrium. In all of the scenarios above, because he is at a constant velocity, whether it is 6 to the right, 3 to the left, 0, or 1.5 to the right, they're all constant velocity. Finally, the way you should really make sense of all these scenarios, how do you maximize the resultant? Look up here at the first one. The biggest resultant was 6 meters per second. That's when they pointed together. Get your arms right. Boom. This is 90. How do you get them both pointing together? This is Carl. This is the people mover. We've dropped down to 0 degrees. They're both pointing to the right here. 90, 80, 70, all the way down to 0. That's 0 degrees. If you want to have a maximum resultant, they should point, the vectors should point in the same direction. We call that theta 0 degrees. Again, that's start at 90. They're pointing people mover and Carl to the right. You had 6. That was the max resultant. That's 0 degrees between them. If instead you wanted the minimum resultant Was this 0? The minimum result, look how they point. One is to the right, one's to the left. Well, you don't have to do this. One is to the right, one is to the left. Separate your arms. Start at 90. You want to make one right, one left? 100, 110, 120, all the way down to 180. Minimum result will happen when the vectors point in opposite directions. The angle is 180 degrees. Boom! That's that. You're now empowered to do these assignments. And you'll see on Classroom which one I gave to you.